Okay, so yeah, Sanjam provided a great setup for our first session of contributed talks, which will be on large language models. And our first talk will be by Leo De Castro. He'll be talking about privacy-preserving large language model inference via GPU-accelerated FHE. So Leo, please take it away.
Okay, yeah, thanks so much for accommodating the remote talks. Sorry for the technical difficulties. Yeah, so trying to not cut in too far into the break, but yeah, so this is, as Alex said, we're going to talk about GPU accelerated FHE and secure LLM inference using this new implementation. This is joint work with Daniel and Antigone at JP Morgan. So in this talk, I'm going to talk about our extension for OpenFHE that makes use of GPUs. And what we see here is roughly 200x speed up in these key operations that can extend to really any other application. And the application that we apply this to is secure LLM inference. So we implement a GPT-2 forward pass under FHE. I can talk. We're going to go into details about what that circuit looks like later on. And this required an analysis of the LLM activation functions when evaluated under FHE. As we'll see in a bit, you really can't evaluate these functions directly, so you have to come up with some clever with some tricks to accommodate these nonlinear functions. Okay, so let's just go over sort of the high level setting. We're in a secure outsourcing setting, sort of the classic FHE application where we have some client that has some valuable data, but maybe not a lot of local compute. So like a financial institution or a hospital or a law firm or a law enforcement agency. And this cloud server we're thinking of as just some public cloud like AWS or Azure or Google. And the client is going to upload its sensitive data in encrypted form. The cloud server can then perform some useful work over this data using FHE and then output the encryption of the results of this computation. And the thing to really stress here is that this computation can be any arbitrary circuit. So we can do like an SQL query, we can do some statistical analyses, or the application that we're going to be focusing on here is something like a document summarization, where the computation is defined by some AI model. So just in a bit more detail, we have, again, a client and a server. The server has some AI model. We could think of the model as being public, but really it could be a private model that the server doesn't want to leak to the client. And the client can then upload a bunch of documents and say, okay, I would like a summary of all of these documents. The server can then run the evaluation of the document summary query under FHE and get the output, which is the document summaries that it returns to the client. So the goal of this project is a forward pass of the LLM inference under FHE. Okay, so the underlying FHE scheme that we will use here is the CKKS scheme because it naturally supports these like real valued and actually even complex arithmetic, and this will let us support the LLM weights and these intermediate values that are not integers. And it also it's nicer than this finite field embedding that exists in other FHE schemes, where you can naturally lose precision, and you always just sort of keep the most significant bits while letting the low order bits fall into the noise. We only have a very small number of supported operations in this scheme. Our plain texts are vectors, and so we can do component-wise addition over these vectors. We can do component-wise multiplication, and then we can also permute the vector elements. But this is really it. I mean, there's maybe a couple other minor operations like conjugation, but at a high level, this is really all that we can do. And sort of looking ahead, the one natural question is, okay, say you have a nonlinear function, how would you evaluate it? Well, the answer is you need some kind of polynomial polynomial approximation. And this is really a huge part of this project is an analysis of these polynomial approximations. Okay, so let's talk about the LLM architecture. So an LLM is mainly consisting of transformer blocks. So we're just going to really be drilling down and focusing on an individual block. We don't have to worry about like the exact architecture of this block, but really the high-level takeaway is that each block is essentially alternating between linear and non-linear layers. As we saw in the previous slide, the linear layers are very easy. You can just run these vectorized multiplications and additions, and the linear algebra of these linear layers really is very, very fast. As we'll see later, it will like barely register in the performance. But for the nonlinear layers, we're going to need to take a look at some approximations. So what are the functions that we would like to approximate? Well, there are three that are the sort of main activation functions throughout the model. The first is softmax, which you can think of as a smooth argmax function. And these nonlinear functions include a comparison circuit to get the max of some vector of elements, an exponentiation circuit, and an inverse circuit. We also have this layer norm function, which is really the key non-linearity is like an inverse square root function. And then finally, we have this Gaussian ReLU, which you can think of it as like a smooth step function. And the main function to approximate here, is a tanh. Okay, so really most of these will use the same underlying tool, which is this iterative comparison approximation. And the reason why this is so nice is because we can evaluate a very high degree polynomial by iteratively applying many fairly low degree polynomials. One issue with evaluating a very high degree polynomial directly is that if you need very high precision from your coefficients, the encryption scheme may have issues handling that. So this really lets you get a very high precision output while maintaining low precision throughout the computation. And right, so what are the like rough depths of these circuits? So the softmax we're going to see as depth 126. This is all, by the way, for an evaluation at position 128 in the output token, but this is sort of a detail. The softmax input fits in less than one ciphertext, and we use some Goldschmidt algorithm for division. The layer norm has depth 51, although the input is spread over 2 ciphertexts, so it takes roughly the same amount of time. And this actually we use Newton a Newton iteration for the inverse square root approximation. And then finally for the GLU, this has relatively low depth because although the input is spread across many ciphertexts. And the reason why the depth is relatively low is because we're really just using a piecewise approximation of the tanh function, where we take the function and we break it up into buckets. Each individual bucket can be well approximated by a low degree polynomial, and then we use the comparison function to sort the input into the appropriate bucket. Okay, so the question though is that because we're not actually running the exact LLM circuit. How does the LLM performance hold up when we take some of these functions and we like swap them out for these approximate versions of the activation functions? And so the way that we went about answering this question was to run sort of standard LLM benchmarks with the activation functions swapped out with the polynomial approximations. And as you can see here, we have a couple different benchmarks that measure both perplexity and accuracy. And the high-level takeaway is that these numbers are very similar. I mean, we had to do quite a bit of work to dial in a lot of the hyperparameters for these approximations to get to these numbers. But the point is that we can get approximations that don't degrade the model quality. This is not a fully general result. This does seem to rely on the fact that LMs don't seem to need very high precision. This is sort of corroborated by some quantization research where you can really squeeze the precision of LLMs and still, get decent accuracy. It would be great to have a slightly more general version of this result where we could say, okay, most of these LLMs, we could, scale this up to like whatever next GPT model comes out and say, okay, we actually don't need super high precision to replicate this under FHE. But okay, we have approximations that work. That's great, but how fast would these actually be? In a CPU, if you want to refresh 20 levels of a circuit, it takes more than two minutes of runtime. And just as a quick reminder, our depths are a lot bigger. And so if we do some back of the envelope estimation on how long these activation functions would take on a CPU, we get like roughly 10 hours of compute time for a single forward pass of the LLM. So that's really not acceptable. And so we need a faster implementation of CKKS. And this is why we turn to GPU acceleration. It's really like the main, one of the main technical tools that we developed is this implementation of CKKS in OpenFHE that makes use of an NVIDIA GPU. And this is fully integrated into the OpenFHE API. And so you can take really any of your LLM application, any of your FHE application and accelerate it with this library. Yeah, so we get this 200x speed up, and yeah, so really part of the reason why we're able to get this level of speed up is we're able to cache all of the evaluation keys. And there's strong evidence that the memory bottleneck persists here. Okay, so we can then take this GPU accelerated FHE implementation and implement our LLM circuit. And what we see is that we get this 200x speed up that carries over. We have we go from about 10 hours to about 2 to 3 minutes for our forward pass. Still not in the realm of like real-time chat, but now these applications of like document summarization and like fine tuning, which I'll mention at the end, become much more feasible. As you can see, the linear layers like barely register. It's a bit skewed because all of the time for the bootstrapping is absorbed into these activation function benchmarks. But really, as you can see, like almost all of the time is spent on the activation functions. We also benchmarked a batched evaluation that makes full use of these vectorized ciphertexts. And this provides significant savings for like the softmax function when the actual input to the function is not very wide, even though the circuit is very deep. And just as a quick note about the security parameter, you can sort of overextend the modulus just a bit for a reduced security parameter, but it'll give you slightly better performance. Okay, so just in like the last minute, the next steps, we would like to scale these inference benchmarks to larger models and also make better use of the past quantization works to implement some, if we get the quantization to be low enough, we don't have to worry about these polynomial approximations. We can just directly look up the outputs. That would give us very, very nice replication of the plaintext circuit. And there's also a lot more opportunities for GPU optimization. We can try to address some of the memory bottlenecks that still exist within the GPU itself. For those of you who are familiar with the CKKS bootstrapping phases, the linear transform at the beginning of the operation takes the same amount of time as at the end of the operation, even though the ciphertexts are about half the time. So really the number of key switching operations is still very much the relevant point here. And then obviously, move to larger GPU systems. Yeah, so I'm not sure. I think I'm basically out of time. But yeah, we would also really like to implement some secure AI model training. And yeah, thanks. If there's any if you have any questions, if you'd like to work on faster FHE or LLMs with lower precision or fine tuning or custom CUDA assembly, please send me an email. Yeah, thanks.
Thanks. Any questions from the audience or Zoom? I have one question.
Sure.
Do you see like how far you can take these approximations while still getting good accuracy? Like, I mean, I guess the furthest you could take it, I guess, is just like a fully linear function, right? But I'm guessing that probably wouldn't work so well.
Yeah. So the approximations, I would say, like you can get quite good accuracy for the approximations, especially if you do this like piecewise approach that we did for the GLU, where you take your function that might be arbitrarily complicated, but you just break it up into buckets, each of which you can approximate very, very well, and then you sort your input into these buckets. I mean, I think at some point it may be worth looking into like a digit decomposition of some of these inputs, but my knowledge is mostly done through scheme switching, which really cuts down on your throughput. So yeah, this is also a nice follow-up question.
Okay, we have one question from the audience. Yeah, I'll repeat it. Yeah.
So since that in reality here the limitation is memory or access to memory, is the model, etc., kept on the main machine? I have to be brought over to the GPU. Is that where the performance is lost in the data moving into the GPU in and out versus the actual computations within the GPU itself?
Okay, so the question was about the bottleneck here. So is it like transferring the memory from like the main machine to the GPU or something else?
So it seems to be something else because we have this 80 gigabyte on-chip RAM, so we can cache all of the rotation keys for the bootstrapping, as well as all of the weights for the model in the clear. We do have to do some on-the-fly NTTs, but that's but yeah. So there are bottlenecks though within the GPU itself. It seems like where like you have like 80 gigabytes of RAM, but there's a hierarchy to these caches before it actually hits the compute unit. And this is where we might have to like write some more manual caching to say, hey, I actually do want these switching key limbs to stick around for a little bit and so on. But yeah, it's just it doesn't seem to be the compute that is the bottleneck. Just because of this observation that you have these two linear transforms, one at the beginning of the bootstrapping and one at the end. One has significantly more compute than the other, and yet they take the same amount of time. And so there's something there that is related to like the data movement of the keys or of the weights for the linear function. So yeah, it's not totally clear where that is yet, or how we can like kind of pull this out and mitigate it. But yeah, it's just an interesting observation, I guess.
Maybe we should take it offline, actually.
Sure. Yeah.
Sorry. How deep is the model you're looking at?
So the model is 12 blocks. So this is the GPT too small. If you have more blocks, the runtime will scale linearly.
All right. Yeah, let's thank the speaker again.
Maybe I'll just stay here.
Yeah, that's fine.
Okay. Thank you. So, hi everyone, I'm Yang Sibo, and today I'm going to talk about our work on achieving user-level differential privacy fine-tuning for language model. So this is a joint collaboration when I was still back in Princeton, and now I joined Google, and with my Google collaborators and also collaborator from University of Washington. I think it's good. Cool. So first thing first, you all know, like language model nowadays have been trained on privacy-sensitive data, and also my colleagues at Google have been shown that you can easily extract this kind of data by using some prompting techniques. And that's the reason why we need some privacy protection mechanism. And the most widely adopted one is differential privacy. And on a high level, I guess most of you already know that, but let me briefly revisit that. So basically, imagine you have original data set, which is noted as D, and you have some kind of analysis or training algorithm on top of D, and you observe the output is O. And imagine you have another kind of data set where you only introduce a single example into the original D, and you get D prime. And now we call D prime a neighboring data set of D. And then you do another round of analysis or training on top of D prime, and you observe output O prime. So what differential privacy gives you as a guarantee is that the output O and O prime are very similar to each other. So in another sense, it means that an adversary who observed O and O prime will not be able to tell whether the single example, which is probably like a privacy sensitive example, has been used in training or not. So this is all the formulation under example level differential privacy. But as you may imagine, in the real world, as a user we chat with language model, we may have multiple conversations. Like some user may have more conversations, some user may have fewer conversations. If you're achieving differential privacy as I just showed you, and you use the model, then unfortunately, users who contribute more example will suffer from higher privacy leakage due to the formulation of differential privacy. And then some users may feel happy, some are not. That's the reason why example level differential privacy will result in unfair user level privacy protection. And maybe we want to think of like a paradigm shift from example level privacy to user level. So as imagine, like on the abstract level, we still have these users. Each of them contribute a different number of examples. And let's say in the middle, we have something called user level DP mechanism. I'm currently putting that very abstract level, but later on, I will tell you what is exactly the thing we can do here. And at the end of the day, like each one is having the same privacy guarantee, and everyone is happy. So, but something we need to always think about in the DP mechanism is like there are also always inherent trade-off between utility and privacy. So in this work, we try to do a comprehensive evaluation of user-level DP design choices in fine-tuning large language model. So basically, we consider various models, data set, and privacy budgets. We try out different user-level DP mechanisms. And also, we try various data selection strategies. In a few slides, we will know why the data selection strategies is very relevant here. And then we reach out some conclusion. But to give you some like result preview before I dive into the actual details, we find like the utility gap between the words and the best design choices could be relatively high. So on the y-axis, I'm reporting the evaluation perplexity. The lower, the better. And on the left-hand side is showing the results for email kind of data sets. You can see the utility gap could be roughly 2 perplexity point, which is very high. And similarly, on the books data set, we can also observe something like that. So how we are able to do that? So let's firstly walk it through like the multiple kind of choice of models and data set and privacy budget we consider in this evaluation. So the models we're considering are mainly like transformer family of model, GPT-2 of various sizes. And the data set we consider are emails and book data set, which are of higher like privacy concerns. And also you will see different dynamics in terms of number of records that each user is contribute to. And we also consider a wide range of privacy budget here, which is denoted as epsilon. And the lower the epsilon is, the better privacy guarantee you're having here. Okay, now for the user level DP mechanism we're considering here, we're basically trying to plug in some DP mechanisms into the DPSGD pipeline, which is the pipeline to train the model using differentially private stochastic gradient descent. The first thing we consider is called group privacy. The idea is actually quite simple. Imagine like we have a data set and each of the user denoted by different colors contribute a different number of data points to the data sets. You can firstly try to do a filtering of the data set such that each user's contribution is upper bounded by some number k here. And then you just try to do the whole training, like the differential privacy training on top of this filter data set as it is. And at the end of the day, you will have the model that gives you a user level DP guarantee. And there needs some way to translate the example level DP guarantee into the user level DP guarantee. And naively, you can do the translation in this way. But also, since we're dealing with a specific case of DPSGD, we can actually benefit from a tighter group privacy bound from this very recent work, which is based on mixture of Gaussian mechanisms. And in our evaluation, we actually try to make the comparison to be kind of fair, such that we use like this more advanced accounting mechanisms. So that's basically about group privacy, very simple. You just do some pre-filtering of the data. Another thing you could do here is something we refer to as user-wise DPSGD. The idea is also not too hard. So like let's say on the fly of training, at each training step, we can try to sample from the user data point of a fixed number or like a varied number of examples. For example, for the blue user, we sample K1 records. For the green user, we sample K2 records. And then we just do that on the fly. And then for each of the user, we do a user level gradient averaging such that we kind of like upper bound the user sensitivity in contributing to the model. And at the end of the day, we do the gradient clipping and also adding noise on top of that. So as you can see for these two mechanisms, it all involves some sort of like data selection. For example, for the group privacy one, you need to pre-filter the data, but this is like the same set of data and you use that across the training. And for the user-wise DPSGD1 on the fly, you also need to do some data selection. And in different training epochs, you potentially are selecting different set of data points, which potentially gives you more diversity in terms of the training data. And then this boils down the third part of the design choices. How can you do the data selection? In our work, we consider various data selection strategies. So as you may imagine, like in the training data, different sequences adopt different lenses, and they also have some like other important statistic bound to that. And in language models, the most important statistics like the perplexity of each single data point. Let's say we want to select among, like, this is a very kind of abstract example. Let's say we have 5 examples like this. We want to select 3 out of them. There are various ways of achieving that. You can either do random selection. You can select the longest sequences, select the shortest one, select the ones with highest perplexity, or select the one with lowest perplexity. Very intuitive kind of design choices. And all of them are applicable to both DP mechanism I just talked about. But there's also something kind of like more interesting that you can apply here, which can only applicable to the user-wise DPSGD mechanism is like something we refer to as random chunk selection. So let's see, we have users who contribute this 5 example. We just patch this 5 example all together, and then we randomly select 3 chunks out of them. Because for group privacy, you cannot actually go beyond the data boundaries, but for user-wise DPSGD, it doesn't matter like what kind of data you're having because finally you're doing user level gradient clipping. So we can actually kind of like going about across the boundary. And later on, we actually observe this can gives you much better performance compared to other selection mechanisms. Okay, so now let's see some results. Firstly, the results for group privacy. On the y-axis is still the evaluation perplexity, the lower the better, and different group bars correspond to different privacy budget values. And we try to do the evaluation, and as you can see, the longest selection gives you the best performance across all the privacy budget we're evaluating on. And we also try to see how many records we should, or how many examples we should select for each user. And we find like smaller smaller number of examples selecting per user is generally achieving better results for smaller epsilon, while larger epsilon actually favors larger K. And we find consistent results across various data set and also model sizes. And then for user-wise DPSGD. So as I just told you, we observe like selecting the random chunks gives you actually the best performance because you can try to have more diverse data selection by going across the data boundary. Different from the group privacy, we find usually having a larger K gives you, in general, better performance for user-wise DPSGD. We also try to do more kind of like side-to-side comparison between group privacy and user-wise DPSGD. And we find in general, user-wise DPSGD outperforms group privacy, especially for smaller privacy budget, which gives you higher privacy guarantee. And some number on the computation costs, user-wise DPSGD slightly incurs higher computation costs because you need to do the on-the-fly selection, but all of them are kind of still acceptable. And putting together again by just trying various different ways of doing the data selection and try to see what kind of mechanism here is better, we're able to identify in the like it's not kind of worse, it's more kind of like more naive way of doing the DP fine tuning, and the best way of like doing user level DP fine tuning. The utility gap is actually quite high. Okay, so in this work, we try to study language model fine-tuning using user-wise DP guarantee, and we try to identify two different mechanisms of achieving that, and we find that the data selection strategy is actually very important in improving the privacy and utility trade-off. And in our work, in the paper, we actually do another kind of like case analysis. So there's a recent algorithm suggesting that it can give you optimal exact rate for user-wise DPSGD, but we actually show that the assumption in this work might be too restrictive for real-world user-level DP applications. And for future work, I think there's definitely something we haven't explored in this work. For example, currently for most of the evaluation, we're fixing the number of K, which is the number of examples we select for user. We can try to explore more dynamic choice of K. And also there might be some other not less naive or less intuitive ways of selecting data. For example, if you try to use some sort of grading information in a private way or use active learning in a private way, maybe you can achieve better utility and privacy trade-offs. Yeah, so with that, I would like to conclude the talk, and I'm happy to have any questions.